This is your presenter, Asloob Mudassar, and I am presenting slide number 4 of the course on atomic and molecular physics. Today, the following topics will be covered: spectra of hydrogen-like atoms, Sommerfeld causal displacement law, muonic atoms, muonic transitions. Spectra of hydrogen-like atoms. According to Bohr, the spectra of all atoms or ions with only one electron outside the closed shells of electrons is the same, except for the factor Z square and the Rydberg constant, which differ from atom to atom. Thus, helium singly ionized, lithium doubly ionized, beryllium triply ionized, etc., have spectra which can be explained by hydrogen spectrum. For helium singly ionized, we can write the Rydberg constant for the helium singly ionized atom, represented by R with a subscript He, is equal to Z square times the Rydberg constant of the hydrogen atom. So putting the value of Z is equal to 2 for the helium atom, we can say that the Rydberg constant of the helium atom is equal to 4 times the Rydberg constant of the hydrogen atom. Astronomers found Fowler series for helium singly ionized as given below. The Fowler series for the helium singly ionized atom is represented by nu F bar. This nu bar represents the wave number and the subscript F represents the Fowler series. So this is the wave number of the Fowler series on the left hand side of equation 4.1, and on the right hand side we have Z square times RH and times 1 over 3 square minus 1 over n square. So actually this is the formula that explains the transition lines in the Fowler series. And substituting the value of Z is equal to 2 for the helium atom, we have on the right hand side that nu bar F will be equal to 4 times the Rydberg constant of the hydrogen atom, and within the parentheses we have 1 over 3 square minus 1 over n square. And for this Fowler series we have n is equal to 4, 5, 6 and so on. So this is the Fowler series. So you see that the formula is very similar as we have seen such a formula for the case of the hydrogen atom. So this is the case of hydrogen-like atom. Particularly, we are talking about the helium singly ionized, and you see that except for the factor 4, which is present over here, and the rest of the quantities are very similar to those of the series in hydrogen-like atoms, in the hydrogen atoms. And there was another series which is called the Pickering series for the helium singly ionized atom, and the Pickering series is represented by capital P as a subscript on the wave number nu bar. So we have nu bar with a subscript P is equal to 4 times the Rydberg constant of the hydrogen atom, and within the parentheses we have 1 over 4 to the power 2 minus 1 over n to the power 2. So you see that this is the formula that explains the Pickering series obtained from the helium, from singly ionized helium, and the principal quantum numbers n varies in this formula given by n is equal to 5 and 6 and 7 and so on, as given in equation number 4.2. You see that we can also modify formula 4.2 in a more appropriate form as given in equation number 4.3. So the wave number for the Pickering series, which is nu bar P, is equal to RH, and the 4 that is the factor 4 which appears on the right hand side in equation number 4.2. I have multiplied 4 inside the parentheses, and the parameters in the parentheses could be written as 1 over 2 square minus 1 over n by 2 square. You see that I have written this one because I want to take some useful information out of equation number 4.3. That's why I have written the second term as the square of n by 2. And again, n varies for the Pickering series as 5, 6, 7, 8, and so on, as shown in equation number 4.3. Now you see that here I have, if I choose even values, even integer values for the values for the principal quantum number n, I can write that for even values n will be equal to 6, 8, 10, and so on. And n by 2 will be equal to, the half of 6 is 3, half of 8 is 4, half of 10 is 5, and so on. So these are actually the even values from the original principal quantum number values, and I have written that one as n even is equal to n by 2 is equal to 3, 4, 5. This n even means that originally the principal quantum number had even values, and now I have taken those values as n even values equal to n by 2, and then I have written these values as 3, 4, 5, and so on. Now you see that I have modified the formula given in equation number 4.3. So you can compare the formula given in 4.3 with the formula written in 4.4. So you see that this is the same formula as written, but I have introduced the new principal quantum number as n even. And of course, the values of the n even has also been written in equation number 4.4. That is, n even will be equal to 3, 4, 5, as I have just explained. So you see that you can recognize the equation number 4.4, that the formula given in equation number 4.4 is nothing but the same formula as for the Balmer series of the hydrogen atom. But you see that here we have chosen only selective number of principal quantum numbers, which we have regarded as n even. But in principle, they are 3, 5, 4, and so on. So you see that in the Balmer series formula, we have the same value of principal quantum numbers 3, 4, 5, and so on. And at the first position we have the quantum number equal to n is equal to 2, because all the transitions will be from the higher levels to the level number 2 in the hydrogen atom, giving you the Balmer series formula. So actually this is the same formula as the Balmer series formula. But you know that this formula is what we have obtained from the Pickering series formula. And by selecting n is equal to 6, 8, 10, and so on, which we have made as n even to be equal to 3, 4, 5, and so on. So the equation number 4.4 represents the Balmer series formula. So this is the same as Balmer series formula, except that it is valid for even values of n from the allowed values of n for the Pickering series were 5, 6, 7, 8, 9, 10, and so on. And you see that I have shown the even values in the red. So 6 is in the red, 8 is in the red, 10 is in the red. And for these even values from this original series of principal quantum numbers, I have chosen the n even values, which is equal to half of these even values, which are 3, 4, 5, and so on. And these satisfy the same formula as given for the Balmer series of the hydrogen atom. So let me read again this, that this is the same as Balmer series formula, except that it is valid for even values of n from the all allowed values of n, which are 5, 6, 7, 8, 9, 10, and so on. That is for n even, as given in equation number 4.4. The lines due to odd n values, which were 5, 7, 9, and so on, from the allowed values of n, the other values which were odd values equal to n is equal to 5, 7, 9, and so on, will exist between the even n values. So the spectra with the even n values will be similar to the Balmer series formula. So let me summarize once again from the original formula of the Pickering series given in equation number 4.2. You see that I have 5, 6, 7, 8, 9, 10, and so on. These are the allowed principal quantum numbers, and I have converted this formula into the formula of the Balmer series with the initial index is equal to 1 over 2 to the power 2, and the second index is 1 over square of n by 2. And I have used even values from the allowed values of the principal quantum number to show that these satisfy the same values as for the Balmer series formula. The odd values, of course, which are left unused, that is the odd values which are 5, 7, 9, 11, and so on, these values will lie between the odd values. So the spectral lines corresponding to the even values will be there according to the Balmer series formula, and the odd values in 5, 7, 9, and so on will lie in between those even values. So now I am going to present a table where I have shown the values obtained from this formula. For example, the Pickering series is shown on the left hand side with the change of quantum numbers from n to n prime. And you see that the quantum numbers will change from 6 to 2, then from 5 to 2, which I have not shown, from 6 to 2, then from 7 to 2, and the next one which I have shown is from 8 to 2. The next one will be from 9 to 2, which I have not shown. The next one is 10 to 2, which I have shown. The next one will be from 11 to 2, which I have not shown. And the next one, which is from 12 to 2, I have shown. So I have shown the even values of these one, because these even values will correspond to the values of the bumped series formula. And you know that I have also shown the wavelength for the singly ionized helium atom. So the wavelength which will be emitted under the transition from 6 to 2 will be 656 to 60.1. For the odd values which will be under the transition from 7 to 2 will be 5, 4, 11, 5411.6. And for the transition from the principal quantum number 8 to state number 2, the emitted wavelength will be 4859.3, and when the transition from 9 to 2 will take place, the emitted wavelength will be 4561.6, and under the transition from change of a principal quantum number from 10 to 2, the transition wavelength will be 4338.7, and under the transition from 11 to 2, the wavelength will be 4199.7, and under the transition from principal quantum number 12 to state number 2 will be 4100. Now, on the next column, I have shown the values for the hydrogen atom, and these wavelengths are in the angstrom. And on the extreme right hand side, I have shown the change of a principal quantum numbers for the Balmer series, which will be from the change of a principal quantum number 3 to 2. The first wavelength that will be emitted will be 6562.8, and you know that this wavelength is referred to as the H alpha line for the Balmer series. The next line from the Balmer series will be under the transition from the principal quantum state from 4 to 2, and will give you a wavelength of 4861.3, and this wavelength is regarded as H beta line. The third line will be under the transition. The third line of the Balmer series under the transition will be from quantum state 5 to quantum state 2, will give you a wavelength of 4340.5, and this wavelength is referred to as the H gamma line. The fourth line of the Balmer series will be under the transition from 6 to 4, and the wavelength emitted will be 4101.7, giving you the line which we call as H gamma line, H delta line. So you see that I have shown H alpha line, H beta line, H gamma line, and H delta line, shown in colors red, green, and you can compare the Balmer series from the hydrogen atom with the Pickering series for even values of transitions from the singly ionized helium atom. You can see the first row of the wavelengths gives you for the helium singly ionized as 6560.1, and the hydrogen atom gives you 6562.8. So you see that there is a small value of difference between the two values. And you see that this is a slightly reduced value from the helium singly ionized value in comparison with the wavelength with the H alpha wavelength from the Balmer series. The other value that we can compare is the green wavelength under the Pickering transition from 8 to 2, and under the Balmer series transition from 4 to 2, giving you a wavelength of 4859.3, whereas the wavelength that is obtained from the Balmer series of the hydrogen atom under the transition from 4 to 2 is 4861.3. Again, you will notice that there is a small reduction in the value of the wavelength obtained from the helium singly ionized atom. The next transition, the next wavelength shown in the red for the H gamma line from the Balmer series is 4340.5, whereas the same wavelength emitted by the Pickering series is 4338.7. Again, you will notice that the wavelengths are fairly close to each other, but there is a small reduction in the wavelength from the helium singly ionized atom. The last wavelength for the comparison is shown in green, which we call as H delta line from the Balmer series of the hydrogen atom under the transition from 6 to 2, and the wavelength emitted is 4101.7, 4101.7, and the wavelength corresponding and the corresponding wavelength from the Pickering series is 4100. Again, you can see that the two wavelengths are very close to each other, but there is a small difference, but there is a small lowering value obtained from the helium singly ionized atom. So here we can see that the Pickering series for even values of transitions can be are very well close to the wavelengths obtained from the Balmer series of the hydrogen atom. But though there is a small difference between them, and the small difference is in the lowering values, slightly lower in the lowering values obtained from the Pickering series. And you know that the rest of the values, the Pickering series formula that I have modified over here, which is shown in equation number, which is shown in equation number 4. You can see this formula is has a great resemblance with that of the Balmer series formula. In principle, the formula is the same as that of the Balmer series formula, and but the odd values, the original values were taken as even values. That is n is equal to 6, 8, 10, and so on. So from the original set of allowed n values, I have taken even values for the comparison with the Balmer series. The odd values are given over here, and I have not specified. For example, the wavelength 5411.6 in the Pickering series, the second wavelength obtained under the transition from the quantum state 7 to quantum state 2 is this wavelength, and you see that this wavelength, since is not for a comparison with the wavelengths from the Balmer series, so I have not specified the corresponding principal quantum numbers from the Pickering series, but just only the wavelengths has been specified, that these wavelengths lie between the two levels of the Balmer series, or the two values corresponding to the even values of the Pickering series. The odd values lies in between them. So it means that we can explain the other series. For example, we can explain the Fowler series. We can also explain the Pickering series, and I have chosen one series, that is the Pickering series, to elaborate it further and compare it with the Balmer series formula. Now you see that the same comparison is given in terms of the diagram. So this is the energy level diagram in terms in the atoms of hydrogen, helium singly ionized atom, and lithium doubly ionized atom. So these are the energy levels I have shown. You can also say that these are the term diagrams. So on the left hand side we have plotted the energy in electron volt, and you see that these are the binding energies of the electron shown in negative, 0, then minus 20, minus 40, minus 60, minus 80, minus 100, and minus 120. These is not following a linear scale, but I have drawn them so that I can elaborate some lines over here in this region, whereas the other regions need no elaboration in this region. So I have compacted the scale on the energy scale on the left hand side. And you see that I have also given, for example, minus 13.6 electron volt is the ionization energy of the hydrogen atom. Or you can say that minus 13.6 is the binding energy of the first orbit of the electron. And then you can see that the binding energy, which is minus 54.4, is the binding energy of the closest electron in the helium singly ionized atom. And for the lithium doubly ionized atom, the binding energy of the closest electron is minus 122.5. These are the binding energies of the closest electron of the closest orbit to the nucleus. for these hydrogen atom, for the helium atom, and for the lithium atom. Now you see that this is for the hydrogen atom, and I have shown only few levels in the hydrogen atom which are important. For example, the level number 1 corresponding to n is equal to 1, the level number 2 corresponding to n is equal to 2, level number 3 corresponding to n is equal to 3, level number 4 corresponding to n is equal to 4. I shall be discussing these levels, that is level number 2, level number 3, and level number 4 in detail, because all the transitions which occur from higher quantum states to the level number 2 form the Balmer series. That's why in the Balmer series, the lowest levels is the level number 2, and the other levels, the high levels, the allowed higher levels are level number 3, level number 4, level number 5, and so on. So in the helium singly ionized level, for example, this helium singly ionized levels which I have shown, which are important for me, I have shown the level number 2, then the level number 4, 5, and so on, these levels are present. Then the level number 6 I have shown, and then I have missed level number 7, and then I have shown level number 8. So I have marked only even levels. So I have shown level number 2, I have shown the allowed level number 6, I have shown the allowed level number 8. And then you see that if I consider the Pickering series in the form of the Balmer series, then of course the transition will occur from level number 6 to level number 2. The next transition will be from level number 8 to level number 3. And you know that I have converted these even levels. For example, level number 6 was converted to even number by dividing it by 2. So this in actually in comparison with the Balmer series formula, this 6 becomes equal to 3, this 8 becomes equal to 4 for the comparison. So you will notice that the difference in the energy between the level 2 and level 6 of the helium singly ionized level is the same as the difference between the level number 2 and the level number 3 of the hydrogen atom. Similarly, the difference in energy between the level number 2 and the level number 8 of the helium singly ionized atom, the difference between these two levels is the same as the difference between level number 2 and level number 4 of the hydrogen level atoms. So that's why there I have discussed as before in the table before, that is the Pickering series is satisfying the wavelengths very close to the Balmer series, and these levels I have shown in red. That is the transition from 6 to 2, and the transition from 8 to 2 will give you the same energy as the transition from level number 3 to level number 2 of the hydrogen atom, and the level number 4 or to level number 2 of the hydrogen atom. I have not discussed the lithium doubly ionized atom, but I have shown the first two levels, three levels of these over here. That is level number 2 has been specified, level number 3 has been specified. But since I have not discussed the helium doubly ionized atom, so I am not going to discuss them, but only I am going to make a comparison of the spectral lines of the helium singly ionized atom and with that of the hydrogen atom, especially with the Balmer series from the hydrogen atom and the Pickering series from the helium singly ionized atom. These have been compared in the table before, and these have been shown over here in terms of the term diagrams. Other series for the helium singly ionized atom were found later on. For example, the first Lyman series, represented by a new bar with a subscript L1. L1 stands for Lyman series 1, is given on the right hand side as 4 times H, RH. RH is the Rydberg constant for the hydrogen atom, and then this series is 1 over 1 square minus 1 over n square. And here n starts for 2, 3, 4, and so on. That's why it is called it is very similar to the Lyman series, except that we have a factor 4 over here in equation number 4.4. And then the second Lyman series is what we have a new bar with a subscript L2, and that is equal to 4 times Rydberg constant of the hydrogen atom, and within the parenthesis we have 1 over the square of 2 minus 1 over the square of n. And here n starts from 3, 4, 5, 6, and so on. You see that I can convert the formula given in equation number 4.5 to the formula shown in equation number 4.6 by multiplying the factor 4 inside the parenthesis. And again, you will see that if you consider the even values of n from these allowed values, then you can see that this will satisfy the original Lyman series formula. Here the condition is that n must be even values from all these allowed values. You need to choose the even values, that is n is equal to 4, n is equal to 6, n is equal to 8, and so on. Then of course putting these values, you will see that this is identical with the standard form of the Lyman series formula. So for even values, this will satisfy the Lyman series formula, as the Pickering series formula for even values were equal to the Balmer series formula. So you see that similarly, these two formulas, that is the Lyman series formulas given in equation number 4.4, and for some selected even values of allowed values of n, for even values of n as given in equation number 4.6, satisfy the standard Lyman series expressions. Now equation 4.6 matches with the original Lyman series for even values of n, and the difference in values will be negligibly small. Again, there will be a difference, but the difference will be very small, and the difference will be explained. Why the difference is because the nuclear charge for the helium singly ionized atom is heavier. Nuclear charge is heavier than that of the hydrogen atom. Then due to that one, there will be a small shift of these wavelengths towards the downside. As you know that, as explained in this table, that is, there is a small difference of the wavelengths obtained from the singly ionized helium atom, that there is a small these values are slightly lower than the corresponding values of the Balmer series, and this fall and this small reduction in these values is because of the heavy nuclear charge of the helium singly ionized atoms. Similarly, for the Lyman series over here, since these are obtained for the helium singly ionized atoms, then because of the heavy nucleus comparison with the hydrogen atom, there will be a small shift of wavelengths towards the downside, but of course the wavelengths will be roughly equal to each other. Note that the Rydberg constant for a hydrogen-like atom having atomic number Z denoted by RHZ. So RHZ means that this is the Rydberg constant similar to the hydrogen-like atoms. So RH stands for the hydrogen-like atoms having atomic number Z is given by. So on the left-hand side, we have the Rydberg constant for the hydrogen-like atom having atomic number Z, that will be equal to Z square times the Rydberg constant of the hydrogen atom as given in equation number 4.7. Now the next we are going to discuss the Sommerfeld causal displacement law. This was discovered in the year 1919. It states that the spectrum of an ionized element is similar in structure to the spectrum of the neutral element preceding it in the periodic table, provided the number of electrons are the same. So if you have an ion with the same number of electrons as the element just before that one in the periodic table, then both will have a similar spectrum. So let me read again. It states that the spectrum of an ionized element is similar in structure to the spectrum of the neutral element preceding it in the periodic table, provided the number of electrons are the same. For example, so I am giving you some examples so that I can elaborate this one. The neutral carbon atom has 6 electrons in around the nucleus. Nitrogen, singly ionized nitrogen, also has 6 electrons. Doubly ionized oxygen atom has also 6 electrons. So all these, that is carbon, singly ionized nitrogen, doubly ionized oxygen atoms, all have 6 electrons around the nucleus and have similar spectra. But the spectra of the heavier nuclear charge will shift towards shorter wavelengths. That is, the spectra of nitrogen singly ionized will shift to shorter values. The values will be more or less the same, but there will be a slight shifting in the values of the spectra of the nitrogen singly ionized. towards shorter wavelengths. Similarly, the oxygen doubly ionized spectra will be very similar to the spectra of the carbon and the singly ionized nitrogen, but will be slightly shifted towards the shorter wavelengths due to what? Due to heavy nuclear charge, because the other atoms, for example, singly ionized nitrogen and doubly ionized oxygen have heavier atoms, have heavier nuclei. The spectra of the helium singly ionized, lithium doubly ionized are identical or similar to the hydrogen, as all have one electron around the nucleus. But since helium singly ionized has a higher nuclear charge than the hydrogen atom, there is a shift towards the shorter wavelengths in the spectrum of the helium singly ionized atom. And you know that this is what I have in the previous table, that where we have compared the values of the Pickering series of the hydrogen of the helium singly ionized atom for the even principal quantum numbers with that of the Balmer series of the hydrogen atom. We have seen that there was that more or less the values were the same from the Pickering series, but there was a slight shift of those wavelengths towards the shorter wavelengths, and the reason has been given in this slide. The spectrum of a neutral atom is related to the spectrum of singly ionized spectrum of the next element. So you see that this is the same statement as we have given above, but slightly in a different form. That is, the spectrum of a neutral atom is related to the spectrum of singly ionized spectrum of the next element. This establishes similarities in electronic configuration and valency. So you see that this way you can determine by a comparison of the spectra, you can determine the electronic configuration of an unknown atom, and also you can find out the valency of those unknown atoms in the form, either in the form of neutral atoms or in the form of ionized atoms having same number of electrons. So since such atoms have same number of electrons with similar spectra, then of course we can by inspection we can find out the electronic configuration of such atoms and also the valency of such atoms. So you see that this last statement is actually the same statement as we have made earlier, but you see that presented in slightly different form. Now I am going to discuss the muonic atoms. So the discovery of muonic atoms was reported in the year 1952. So an electron, you know that in electrons, we have electrons in an ordinary atom. We have, or ions, we have electrons surrounding the nucleus or revolving around the nucleus. But you know that in the muonic atoms, instead of electron, we talk about a heavier particle, which we call as muon, which has the same charge like that of the electron, but its mass is 207 times greater than the mass of the electron. So, when an atomic nucleus captures such a particle, which we call as muon, then such an atom is called muonic atoms. And muonic atoms also have very interesting parameters, and their spectra can also be explained similar to the spectra of the hydrogen-like atoms. That's why here we are studying the muonic atom. So let's start. An electron E is replaced by muon, which we represent as muon by the symbol muon, having a mass of 206.8 times heavier than that of the electron. These particles, which call as muon, also known as mu meson. Muonic atoms are extremely smaller than ordinary atoms, because when an atomic nucleus will capture a muon particle, then due to very heavy mass, its orbit will be very close to that of the nucleus. That's why I have said over here that muonic atoms are extremely smaller than the ordinary atoms. In extreme cases, hardly larger than the typical diameters of an atomic nucleus. So you see that in extreme cases, hardly larger than the typical diameters of an atomic nucleus. So it is very rare that a Muonic atom has a diameter hardly larger than the typical diameter of an atomic nucleus. Now the question is that how to produce muon atoms or Muonic atoms. This is what I am going to discuss next. So you see that the matter is bombarded with energetic protons having an energy of the order of 440 million electron volt, which gives off elementary particles including pions. So here I am going to discuss some reactions which will help us to understand the production of muon particles. So the first one is given in equation number 4.8. This is the proton and this is energetic proton colliding with the neutrons of the matter. So the one possibility is that this proton is converted into neutron with an emission of a particle which we call as a pi positive. So positive pion. You know that this emission of a positive pion having a charge, having a positive charge equal to that of the positron will satisfy the quantization of charge on both sides of this equation. The second possibility is that this energetic proton having energy of the order of 440 million electron volt when collide with the matter, when collide with the neutron in the matter, this proton is converted into another proton. So this neutron is converted into proton. So we have two protons on the right hand side of equation number 4.9 with the emission of a negative pions. And this negative pions has the same charge as that of the electron. And again, you see that the charge quantization is fulfilled on the right hand side and as well as on the left hand side of equation number 4.9. So you see that in both of these equations, which are both likely to be hold when there is an bombardment of the matter by the energetic protons, both are equally possible. And you see that there will be an emission of positive pions and negative pions as shown in equation number 4.8 and for equation number 4.9. The pions represented by pi have charge either E plus or E minus. That is the charge of the positron or that of the electron. And mass m pi is equal to 273 times the mass of the electron. Pions decay into muons. Now you see that these are the pions that were generated in the reaction shown in equation number 4.8 and 4.9. But these pions will decay immediately to the particles which we call as muons. So positive pion will decay into positive muon with the emission of another particle which is called mu neutrino. So neutrino, this is mu neutrino. The second is that the negative pion will decay into negative muon as shown in equation number 11 and also with an emission of a particle which is anti mu neutrino. So this is the anti neutrino and the mu symbol corresponds to that is emitted in the process of production of negative of mu particles. That is why here it is called anti-mu neutrino. And the emission of neutrino in equation number 4.10 and in equation number 11 actually satisfies the quantization of you see that the charge is already quantized, but these are the particles which are the chargeless particles, and of course these particles are emitted as neutrino, mu neutrino and anti-mu neutrino respectively shown respectively in equation number 10 and 11. So you see that up to equation number 10 and 11, we have shown that the mu particles with the positive muons and negative muons are generated in the reactions shown in equation number 10 and 11. So you see that this symbol nu will be represented as neutrino. Nu bar will be represented by will stand for anti-neutrino. The symbol mu as a subscript with the nu will represent as mu neutrino, and the subscript e with the nu will represent it as electron, that is e neutrino or electron neutrino. Muons mu have charge equal to that of the charge of the electron, and the mass of mu is equal to 206.8 times the mass of the electron, with a half-life of 2.2 into 10 to the power minus 6 second. So this is what mu we are talking about, because this mu will be used in the process which we call as muons or muonic atoms or muon atoms. So we shall be using those muons which have charge equal to that of the electrons, and of course the muons will have a mass equal to 207 point times the mass of the electron, and half-life is of course is 2.2 into 10 to the power minus 6 second. Now let's proceed further. Mu plus or positive muon will decay into positron, giving a positron has a charge of E plus. And similarly, this negative muon will ultimately decay into electron, giving a charge of equal to electron as E minus. And you see that here I have described the decay of these particles, that is the decay of positive muon and negative muon. So the first equation given in equation number 12 gives you that positive muon will decay into positron plus emission of two neutrino. One is the electron neutrino and the other is the anti-muon neutrino. And in equation number 13 we find that the negative muon will decay into electron plus it will emit two particles with the anti-electron neutrino, and the second one is a mu neutrino. So these two particles will be emitted in the process. That's why I have described these particles very briefly in the above. So you see that muons will also decay ultimately into these positron and electron. And since we shall be talking about this muon, which has a negative charge, especially equation shown in equation number 13. So this negative muon will decay into the electron because it has a negative charge, and this will be captured by the atomic nuclei to form the muonic atoms. So muon with a negative charge will be captured by the atomic nuclei, and then of course the resulting atom will be muonic atoms or muon atoms, because the negative muon will have a same charge as that of the electron. And ultimately equation number 13 will tell you how the negative muon will ultimately decay in a lifetime as given above. Before muons decay, they can be captured into outer atomic orbits. So you see that once the muon is generated, they may be captured by outer atomic orbits, in the outer atomic orbits by an atomic nuclei, and can occupy electronic orbits replacing electrons. So a negative muon can be captured by the atomic nuclei to form the muonic atoms. When muons make transitions, so you see that once these particles, that is a muon, negative muons are captured by the atomic nuclei, they will revolve around the nucleus, and they can also make a transition from the higher quantum states to the lower quantum states, that is they can come closer to the nucleus by emitting stronger photons or more energetic photons. So when muons make transition from outer to inner orbits, the muons radiate light of the corresponding atomic transition frequency, normally in the X-ray region of the spectrum. Considering muons, mu s, your s stands that we are talking about more muons. So considering muons as heavy electrons, Bohr's atomic model would then be applicable. Bohr's radius of an electron in a hydrogen-like atom of atomic number Z can be written as as we have written for the first time in equation number 3.4, and now we are writing it again as given in equation number 4.14. So on the left hand side we have Rn, that is the radius of the nth orbit of the electron, and E stands for the electron, will be equal to, and this is what we are talking about, the hydrogen like atom is equal to 4 pi epsilon naught multiplied by the factor containing n square h bar square in the numerator and m naught z e square in the denominator. And this Z, capital Z, indicates that we are talking about the atomic, we are talking about the hydrogen-like atom. And if you put Z is equal to 1 over here, then equation number 14 reduces to that of the radius of the hydrogen atom. Now for the muonic atoms, what we need to do is that we need to replace the hydrogen, the mass of the electron by the mass of the muon as shown in equation number 15. M naught has been replaced by M mu, and on the left hand side I have also changed that Rn with the subscript mu. That is, I am talking about this nth, this is the nth orbit of the muonic atom. So that's why muon as a subscript has been written with Rn. And you know that on the right hand side I have the same parameters as given in equation number 14, except that I have replaced the mass of the electron with the mass of the muon. And you know that the mass of the muon is 207 times the mass of the electron. So representing it as in terms of the mass of the electron, I have a factor which is 1 over 207, separated from the rest of the parameters. So I can introduce equation number 14 in equation number 16, and I can write that the radius of the nth orbit of the muonic atom is equal to the radius of the nth electronic orbit of the hydrogen-like atom divided by 207. It means that the muonic atom has a radius which is 207 times reduced reduced in comparison with the electronic radius of the corresponding state of the hydrogen-like atom. That is, the radius of the muonic orbit is reduced by a factor of 207 compared to the electronic orbit. That is, the muonic atoms have reduced size, very compact size, you know. Let's compute the radii of electronic and muonic orbits in magnesium atom. You know that the magnesium atom has Z is equal to 12, and the energy is liberated in an identical transition. So here we are going to compare the radii of the electronic and the muonic atoms and the muonic orbits for the magnesium atom. That is, the magnesium has converted into the muonic atoms by capturing a muon. So we want to see that what is the difference between the difference between the radii of the electronic magnesium atom and the muonic magnesium atom. And also we wanted to compare the transitions between identical states, that is E in the transition from state number 2 to state number 1. So here you can see that equation number 4.17 has been written, and this will give you the electronic radius of the nth state of the hydrogen-like atom having atomic number Z. On the left hand side I have shown these parameters, and on the right hand side I have 4 pi epsilon naught times n square h bar square over m naught Z times E square in the denominator. And you see that this is what I have discussed earlier. Now the first Bohr atom for the hydrogen atom. For the hydrogen atom I need to put n is equal to 1. I need to put capital Z is equal to 1. And I need to, for the first state, for the first Bohr atom, I need to put n is equal to 1. So substituting these values, the first Bohr, the first orbit, the first radius of the hydrogen atom will then be equal to 0.53 angstrom. This has also been calculated in one of the previous slides. Now the first electronic orbit for the magnesium atom. So I am using the same formula as equation number 17. I am using n is equal to 1 in equation number 17, and I am putting z is equal to 12 in equation number 17, so that I can calculate the radius corresponding to the first orbit, electronic radius corresponding to the first orbit of the magnesium atom. So it is given by this relationship. So you can see that the factor of 1 over 12 is present over here. So then I have 0.53 divided by 12, which will give you 4.5 into 10 to the power minus 12 meter, because I have converted angstrom into the meter, and 1 angstrom will be equal to 10 to the power minus 10 meter. Now I am going to calculate the first muonic orbit radius for the magnesium atom. And you know that when we are talking about the muonic orbit of the magnesium atom, then what I am going to make the changes is that I am going to substitute n is equal to 1 in equation number 17. I am putting z is equal to 12 in equation number 17, and I am also replacing mass of the electron m0 with the mass of the muon, which is 207 times the mass of the electron. So making these changes in equation over here. So I have this equation which represents the first radius of the muonic magnesium atom. So this is the magnesium atom, but this is the muonic magnesium atom. The first radius of the muonic magnesium atom is equal to the radius of the first electronic magnesium atom divided by 207. Because you know that, okay, and this will give you 2.2 into 10 to the power minus 14 meter. So you see that here you can see that the radius is much reduced of the magnesium muonic atom has a much reduced radius in comparison with the magnesium electronic orbit, the first orbit. I have compared the first orbit of the muonic magnesium atom with that of the electronic magnesium atom. Now you see that from equation number 3.18, which was discussed in the previous slide, the energy expression for the transition from n to n prime is given by this relationship. So this is the relationship that I have already discussed in equation number 3.18. Now I can convert this relationship into a more appropriate form by the rearrangement of parameters, and the result is given as. So this is the energy of the electronic atom when it makes a transition from n to n prime, having an atomic number equal to z. So this expression on the left hand side represents a hydrogen-like atom, electronic atom of the hydrogen type, having atomic number z, and the transition is from n to n prime. And on the right hand side you can see these parameters, m0 mass of the electron, and the rest of the parameters are the same as shown in the above equation, and also shown in equation number 3.18. Now equation 4.18 gives the transition energy when an electron in atom of atomic number z moves from the state n to n prime. The transition energy for a muonic atom is obtained by replacing m0 by m mu. So you see that in the same formula, in the previous formula, you see that I have used the mass of muon, m mu, and I am going to set that value equal to 207 point the mass of the electron shown in red. And after making that substitution, I can write equation number 19 as on the left hand side I have the energies corresponding to the muonic atom, and on the right hand side of equation number 9 I have a parameter 207 times the energies corresponding to the electronic atom. So you can see that again there is a parameter of 207 times. So the energies liberated by a muonic atom is 207 times the energies liberated by the electronic atom in the equivalent states. That is with the same atomic number z and with the same change of quantum states from n to n prime. So pure hydrogen-like atoms are those having single electron around the nucleus, like helium singly ionized atom and lithium doubly ionized atom. These you may call as pure hydrogen-like atoms. But there are atoms, for example, magnesium singly ionized atom can also be treated as hydrogen-like atom, having one valence electron with a complex inner core containing nucleus plus 10 electrons. These 10 electrons in the inner core will try to shield the nuclear charge. The electronic configuration of the magnesium singly ionized atom is 1s2, 2s2, 2p6, 3s1. And you can see that there is a 3s1 as the valence electron contained in the singly ionized magnesium atom. So magnesium singly ionized may be grouped with alkali metals like sodium, because in the sodium we have similarly inner core of electrons which is completely filled, and then we have the valence electron which is lying outside the inner core of electrons. And then that is similar to the case of the magnesium singly ionized atom. So magnesium singly ionized atom can also be grouped with alkali metal like atoms, and the sodium atom is what we shall be discussing in future. Now, since I am going to discuss the magnesium atom, I would like to give you the binding energies of the electrons in the magnesium atom. For the K shell containing 1s electrons, their energies, binding energies varies from 1303.07 to 1311.47 electron volt. You see that I am talking about binding energies, but you must assume that I have a negative sign with these energies. So for the L shell containing two s electrons having energies of the order of 88.62 electron volt, and the p orbital and the p shell having 6 electrons has an energy of the order of 49.73 electron volt, or these binding energies are in negative. And the valence electron which is a 3s electron, as can be seen from the electronic configuration, has an electron energy which is equal to has an binding energy which is equal to 7.65 electron volt. If mu is captured by a nucleus before it undergoes a decay, then later on, immediately after that one, the capturing nucleus which has captured the neutron will also decay ultimately. These muonic atoms are very useful in the study of some quantities related with nuclear physics. So here I just briefly want to mention them without going into detail. That is, the muonic atoms emit X-rays because these have very closed shells, very close to the nucleus. So when the transitions are made in the inner shells, then of course X-rays are emitted. They are interesting objects for nuclear physicists. They can be used to study the details of nuclear charge density distribution. They can also be used to study the distribution of nuclear magnetic moment within the nuclear volume and the nuclear quadrupole deformation. So you see that these are the important parameters which could be very useful for the nuclear physicist. These parameters can be studied using muonic atoms. In equation number 2.1 and equation number 2.2, that is equation number 21 from slide number 2, equation number 22 from slide number 2, and there in those equations, the orbital angular momentum of an electron and its magnitude were introduced, where the orbital angular momentum was found to be a quantized quantity. Now the orbital quantum number L is being introduced. You see that before that in the said equations, that is in equation number 21 and 22 of slide number 2, we discussed orbital angular momentum in vectorial form, and also we discussed its magnitude, and we found that the magnitude of that quantity was a quantized quantity. That is, the magnitude of the orbital angular momentum was a quantized quantity, and its value was given equal to n times the h bar, where h bar is the reduced Planck's constant and n is the principal quantum number. Now you see that corresponding to that orbital angular momentum, I am going to introduce over here the orbital quantum number represented by small l for an atom having involving single electron, and if more electrons are involved in the formation of the orbital angular momentum, then this small l will be represented by capital L. Now the allowed values of this orbital quantum number L are 0, 1, 2, 3, 4, 5 and so on. The maximum value will be equal to n minus 1. So the principal quantum number of the system will restrict its maximum value to be equal to n minus 1. The lowest value will be equal to 0. This quantity cannot be negative. So L, which is the orbital quantum number, will have values from 0 to n minus 1 in integers, where n is the principal quantum number of the system. Now there are term symbols. You see that shortly we shall be talking about the term symbols, which would represent an atomic level in a spectrum. Those we shall be using some terms symbols for such states. That is for each level of the spectrum, we shall be using some term symbols. So these term symbols are due to quantum number L. For example, the quantum number L, as I said earlier, will change from 0 to 1, 2, 3, and so on up to the maximum value of n minus 1. And the corresponding symbols that will be used to extract the term symbols from these quantum numbers will be corresponding to L is equal to, we have the symbol S. Corresponding to L is equal to 1, we shall use the symbol P. Corresponding to T, we shall use the symbol D. Corresponding to 3, we shall use the symbol F. Corresponding to 4, G. Corresponding to 5, H. Corresponding to 6, I, and so on. So these will be the term symbols S, P, D, F, G, H, I that we shall be using when we are labeling a level in a spectrum. And capital L is used when two or more than two electrons are involved in the formation of the total orbital angular momentum of an atom, and the term symbols in capital letters are used. So if L is capital, that is more than two electrons are involved, then of course the resulting L will be capital, and we shall be explaining how this capital L will be found for the two or more electrons. And then when L will have capital values out of these one, then the term symbols that we shall be using will also be capital. That is, if capital L is 0, then the term symbol will be capital S. And similarly, if capital L is equal to 4, the term symbol will be capital G, and so on. Now you see that this figure, although not important for atomic physics point of view, but this is important for as far as the muonic atoms are concerned. So for the completeness, I am going to give you this figure, and I would like to explain this figure. First of all, I would like to read the caption of this figure. Probability of finding a muon. That is a muon at this is what I am talking about, a muonic atoms. And in the muonic atoms, you know that the muon will circle around the nucleus, and this is the probability which is represented by p mu as a function of r. So this will give you the probability of finding the mu around the nucleus at a distance r from the center of the nucleus of a Z atom. So this the above figure is for the lead atom having atomic number Z is equal to 82. Nuclear radius for the lead atom is R is equal to 6.687 into 10 to the power minus 15 meter. So the probability of finding the muon at a distance R is shown for several orbits labeled over each curve. So you see that I am plotting this probability of finding the mu for several orbits which have been labeled on each curve. So you see that over here I have shown, for example, you can see that I have shown the radius of the nucleus as a capital R is equal to 6.687 in the diagram with a dotted line. And the dotted line in the black represents the nuclear charge distribution. So this curve, which is in dotted line, and represents the nuclear charge distribution. And this is the value of R at which the nuclear charge distribution is has reduced to a value of half. So this will give you the radius of the nuclear charge, or the radius of the nucleus, which has a value of capital R is equal to 6.687. And you know that this is also multiplied with a factor 10 to the power minus 15. So you see that on the left, on the horizontal scale, I am plotting 4, 8, 12, 16, 20, 24, and 28 multiplied by the factor 10 to the power minus 15 meter. So this is the R value that I am plotting away from the center of the nucleus. So this is the distance from the center of the nucleus on the horizontal scale. And the corresponding probability is what I am showing on the vertical scale. So you see that the probabilities will vary from 0 to 1.8. And this is not the normalized probability. So you see that I have shown this one, that is these have been shown for different orbits. For example, for the orbit 1s2, I have shown the green line. You see that for this electron, for the muonic, so not this, this is not the electron, this is the muon, because I am talking about a muonic atom. So this muon can come very close to the nucleus. So you can see its probability is very, so it is very high, 1.6. So this, you see that this over here, we have the center of the nucleus. So this can come very close to the nucleus. And this, and after that one, you can see that it is going to decrease, and ultimately this electron cannot exist when the distance from the nucleus is beyond the value of 20 into 10 to the power minus 15 meter. So this will exist before that one. So this muonic atom in this state, that is the muon in this state, or the state is 1s half, where this one in the beginning represents the principal quantum number, and this half represents the total quantum number of the atom. And this symbol S stands that I am talking about the quantum, I am talking about the electron in this state L is equal to 0. You know that this S state, this S symbol corresponds to L is equal to 0. Since we are talking about a single muon revolving around the nucleus in the muonic atom of which atom? That is, we are talking about lead atom. You know that here we have Z is equal to 82, and here we are talking about the lead atom, and the lead atom has captured the muon and forming a muonic atom, and this is for the muon in the captured by the lead nucleus, and this has a capital, this has an angular momentum L is equal to 0, and standing as a single muon particle. And this half value is what I shall discuss later on in the next few lectures. So this is the first orbit of the muon revolving around the nucleus. So this so muon in this configuration, in this orbital state, can come very close to the nucleus, and you know that after that one, as we increase, as we go away from the center of the nucleus, you see that its probability of finding the muon will decrease, and ultimately after a value of 10 to the power, after a value of 19 into 10 to the power minus 15, the probability of finding a muon particle in this state will be equal to 0. The next orbit that I am going to discuss is the p state. So here the electron has a orbital quantum number equal to L is equal to 1. And this is actually 10 must be multiplied by 10 times, because this is what I have, since I wanted to show all those values within this scale, so you can multiply it a value of 10. So this the muonic atom in the 2p half state, you see that can also come to the close to the nucleus, but its value is reduced in comparison with the muonic in the state of 1s half, where the probability is 1.6, and for this 2p half muonic state, it can also come closer to the nucleus, but with the reduced probability, and its probability will be maximum at about the radius of the nuclear charge. So just outside the nucleus, its value is maximum. So the muonic particle, when it is in the 2p half state, will be very close to the nucleus, because we can observe a peak value there, that is the probability is the highest. So if you go beyond the nuclear charge, that is you go further away from the nucleus, you will see that the probability of finding this muonic atom will decrease ultimately. And of course, at a distance of 28 into 10 to the power minus 15 meter, you cannot find this muonic atom to exist in this state around the lead nucleus. Now there is another muonic particle with a state of 2p3 half. And again, this curve should be multiplied with the value of 10 also. And again, you can see that it has a peak value very close to the radius of the nucleus, and its value is again peaked over there with a peak value of a probability of the order of 1.2. And again, you see that the probability, when we go closer to the center of the nucleus, you will see that the probability will decrease, and ultimately this muonic particle cannot approach the nucleus, because its probability at the center of the nucleus is 0. And you see that the peak occurs very close to the radius of the nucleus, and after that you will see that when you move away from the center, from the outside of the nucleus, you will see that its probability that you can find this muonic atom away from the center of the nucleus will keep on decreasing after the peak value existing closer to the nucleus radius. And ultimately this will also you cannot find out this particle, you cannot find out the muonic particle when it has gone beyond the distance of 28 into 10 to the power minus 15 meter. So there is another state that the muonic atom could be in this state also. So the muonic particle could be in the 2d3 half state, and this factor should be multiplied by the factor of this has been multiplied by the factor of 100. So this curve, which is shown in 2p half, was obtained by multiplying this curve with the factor of 10. Otherwise, this is very short. You see that this peak is very short because it has been exaggerated by multiplying it with a factor of 10. And similarly, this 2p3 half was multiplied with a factor of 10 to show so that we can see this curve. And the electron and the muon particle and the muonic particle in the state of 2d3 half was multiplied with 100, so that you can see the curve. Otherwise, this curve is diminishing very small, and you cannot observe this curve. Again, you can see that this curve has a peak value around the value of 16 or 17 into 10 to the power minus 15 meter. And then you see that on either side, you can see that towards the nucleus, this falls and ultimately becomes 0 before it reaches to the center of the nucleus. And away from 16 or 17 into 10 to the power minus 15 meter, you will see that its value will fall, and ultimately the muonic in this state cannot be observed when the distance is greater than 28 into 10 to the power minus 15. And similarly, the muonic particle can also be in the state of 2d5 half, shown in the dotted red line. Again, this curve was obtained by multiplying it with 100. Again, this curve is diminishingly small, and we have multiplied it with 100 so that you can observe this curve. And again, you see that we can also explain this curve in the similar fashion I have explained the previous curves. So you see that this figure shows a term diagram of the muonic atom levels for a nuclear charge number Z is equal to 60. That's for the lead atom. The analogy with the hydrogen atom is evident. However, the transition here are in the energy region of a million electron volt, that is in the region of hard X-rays and of the gamma rays. For the investigation of such muonic atoms, one therefore requires the tools of nuclear physics. Detection of radiation is carried out with scintillators or with semiconductor detectors. So you see that this was all about the muonic atoms, but of course there are something more that we can see over here. So let me read the caption of this one. These are the muonic terms. This is the term diagram for the muonic atom. So these are the muonic terms of an atom with Z is equal to 60. That is, we are talking about again the lead atom. Solid lines correspond to point nucleus. You see that, you can see the solid lines over here. These correspond to the point nucleus, and you can also see the dashed lines over here. Dashed lines correspond to the finite sized nucleus. So if we assume that the nucleus has a finite size, then of course the spectrum will contain dashed lines. And if we assume that the nucleus to be a point source, then of course we have the solid lines over here. And the emission is in the hard X-rays and gamma rays. So for this term diagram, you can see that I have shown the orbital quantum number with the value L is equal to 0, 1, 2, 3, 4, 5, and I have also shown the symbols corresponding to these. These are the symbols. We shall call them as term symbols. So the term symbol corresponding to L is equal to 0 is S, then we have P, then we have D, then we have F, then we have G, then we have H, and so on. And you see that on the vertical scale, I have shown the energy E in billion electron volt. And since I am showing the binding energies, so the energy is 0 at the top. The binding energy is shown in -2, -7, and -10. The scale is not linear. I have exaggerated the scale where I want so that I can show some levels. And you see that L is equal to 0 for this atom. This is the muonic atom captured by the lead nucleus. And you see that this is the first level of the muonic atom when the nucleus is assumed as the point source, and when the nucleus is assumed to has a finite size, then of course this is the first state of the muonic atom. And then you can see that this is the second state represented by the principal quantum number 2, and this is the state again represented by principal quantum number 2, but when the nucleus is shown in dash, but when the nucleus is considered as having a finite size. And then of course I have shown only the solid design above, because I am assuming that the nucleus is considered as point sources, point particles. So this is principal level corresponding to principal quantum number 3, level corresponding to principal quantum number 4, and so on. Similarly, for the P state, so you say that this is the P state, this is the S state, and here we can say that our muonic atom is in the S state, or you can also say that this is the S muonic, this is the S muonic state of the atom. This is the P muonic state. So the muonic atom is in the P state. Next, you can say that the muonic atom is in the D state. That is, the muonic atom is in the F state, in the G state, in the H state, and so on. So corresponding to the P state, you can see that the lowest level corresponding to the P state corresponds to the value of N is equal to 2. And again, you can see that corresponding to P, you have two values. You have you have the level which corresponds to N is equal to T. This N is equal to 2. This level slightly lowers in energy than corresponding to N is equal to 2 value of the S state. Then the muonic atom in the P state having in energy state 2 has a lower energy in comparison with the energy state when the muonic atom is in the S state. So similarly, the dotted state corresponds to N is equal to 2 state, and of course I have also shown the solid lines corresponding to the other higher states of the P muonic atom. So these are the higher states in the higher P states of the muonic atom. Similarly, the higher D states of the muonic atom start from N is equal to 3. So corresponding to the principal quantum number N is equal to 3, this D state starts from N is equal to 3. So this level you can see is also lower in energy in comparison to the muonic state when it is in the p state and when it is in the s state. So when the muonic atom is in the d state, it's that is in the quantum number state 3, it has a lower energy in comparison with its when it is in the p state or in the s state. Similarly, when the muonic atom is in the f state, it has an energy with a level corresponding to n is equal to 4, because the lower levels will not exist in that case, and this will why these will not exist, which will be explained in the next slides. So you see that this level again is lower in energy. That is, the muonic atom in the f state has an energy, has a level, has the initial level corresponding to n is equal to 4, which has lower in energy in comparison with the its d when the muonic atom is in the d state, or when the muonic atom is in the p state, or when the muonic atom is in the s state. Similarly, we can explain the muonic atom to be in the g state or in the h state. So you see that now I am going to show you some transitions over here. So you can see that this is the k alpha state. So I am using the same notations that is used by the X-ray spectra. And you know that in the X-ray spectra, we use the notations K alpha, K beta, L alpha, L beta, K alpha, K beta, K gamma, K delta. Similarly, we have L alpha, L beta, L gamma, L delta. Similarly, we have M alpha, M beta, M gamma, M delta, and so on. But you see that I have shown only two transitions over here. For example, K alpha transition will occur when the transitions from when the P or when the muonic atom in P state moves to the S state, then from the state n is equal to 2 to the state n is equal to 1, it will emit a photon which is called K alpha. So if the muonic P atom, if the muonic P atom in the state P with the principal quantum number n is equal to 3 jumps to S state, S muonic state with the principal quantum number n is equal to 1, it will emit K beta. And K alpha and K beta have energies in hard X-rays. Similarly, you can see I have shown the transition L alpha. So L alpha is the transition when the muonic atom in D state moves toward the P state. That is from the D state with the principal quantum number 3 to the P state with the principal quantum number 2. So under this jump, it will emit a photon, which is regarded as the wavelength is regarded there as L alpha. And similarly, when it makes a jump from the d muonic, when the d muonic atom will jump from the principal quantum number n is equal to 4 to the p state, p muonic state with the principal quantum number 2, it will emit a photon which we label as L beta. Similarly, the next two transitions show M alpha and M beta when the muonic atom from the when the muonic atom in the F state with the principal quantum number 4 moves to the d muonic state with the principal quantum number 3, it will emit M alpha. Similarly, when the muonic atom in state F moves to a muonic atom state in D from principal quantum number n is equal to 4 to the principal quantum number 3, it will emit M beta. So you see that similarly we can show other transitions, but I have shown only limited number of transitions in order to explain that these transitions have been labeled with the similar notations as would be used with the X-rays, that is K alpha, K beta, L alpha, L beta, M alpha, and M beta. So you see that I have explained in this diagram the term the muonic atoms going through transitions captured by the lead atom. So this is the lead-oriented muonic atoms. Now again, I am showing you these plots which are useful for the nuclear physicist, but for the completeness, I am going to show you because I shall not be discussing the muonic atoms later on throughout this course, but only muonic atoms will be discussed in this slide. So I want to show this one in detail. So let me read the caption of these figures. So this is the Lyman series, that is transitions from NP to 1s. You know that in the Lyman series, the transition of the lowest level is always the 1s level, that is the lowest orbit, and NP, the levels, the upper levels can make a transitions. So this is 1p, 2p, 3p, 4p, 5p, and so on, because the principal quantum numbers can take integer values starting from the value of 2. So from 2p to 1s, from 3p to 1s, from 4p to 1s, from 5p to 1s, and so on. These transitions will form the Lyman series of the muonic transitions in a titanium atom with Z is equal to 22. So here we are talking about the titanium Muonic atom, and having Z is equal to 22, and the transitions shown are for the Lyman series. So the first transition is from 2p to 1s, and you see that this is the transition I have shown. And this has been exaggerated by multiplying it with 1 by 10. Otherwise, this was an increased transition, and we have multiplied it with 1 by 10 so that we can reduce its magnitude. The other one is from this transition in black is from 3p to 1s. The next transition shown in green is from 4p to 1s. That is when the muonic atom will make a transition from the 4p to the 1s, it will emit the green wavelengths. And then from the 5p to 1s, it will emit red wavelengths. Then again from 6p to 1s, it will emit a wavelength shown in dark line. And similarly from 7p to 1s, again in dark, and then you see that I have shown in blue, and these represents other transitions, and ultimately the final transitions will be from 14p to 1s. So corresponding to these transitions, you see that these are the transitions which are the theoretical transitions shown by the delta functions. But you know that the wavelength cannot be as small, that is a single wavelength cannot be emitted. Of course, the other wavelengths along that one will be emitted, which are shown in the corresponding spectra over here. For example, this red line, which is shown ideal, this is the ideal transition, or you can say that is the theoretical transitions over here. And this is the actual transition which is shown over here in the form of a curve. So the center of this curve will match with the center of the transition shown over here in the bottom plot, because these the plots in the bottom show you the single wavelengths which at which you obtain the maximum values of the maximum magnitude corresponding to those wavelengths. And here you can show the spectrum, the full spectrum of these one containing other wavelengths also. And the wavelength is also the wavelength in terms of the energy are given, that is this curve will emit in the range of 920 to 440 kilo electron volt. Similarly, corresponding to this one, that is from 3p to 1s transition, that is from 3p to 1s transition, you will obtain this curve. Then for the green curve that which was obtained for the transition from 4p to 1s, you can see that the green profile will emit not only a single wavelength, but many other wavelengths will also be emitted with reduced as you go away from the center of this peak. The magnitude of the other wavelengths emitted along with that one will have reduced magnitudes. And then of course you can see that the other wavelengths are also shown, and then the other wavelengths which are very close to each other, then their spectrum will merge out, and then of course the spectrum will be continuous spectrum showing the other wavelengths very close to each other, and then of course you will come out with a series limit. This is the Lyman series limit, where you will observe the continuity in the levels. That is, the levels are so close to each other that they becomes continuous, and you see that this is the classical limit. We have reached the classical limit where the quantum and the classical, or you can see that where the correspondence principle which we have discussed in the previous slide will hold over here. So this is the series limit, and in the series limit you can see that the levels, though I have made them well apart, but these levels are very close to each other, and we cannot make any distinction between these levels. So you see that this is what I have shown the Lyman series for the muonic atom based on the titanium atom having Z is equal to 22. So you see that I have discussed in much greater detail the muonic atoms, because muonic atoms, as said, that very useful for the study of the nuclear structure. That is the charges. That is the charge distributions around the nucleus, and then of course other parameters. This is what we have discussed also. So you see that in the 2 days lecture, we have discussed very important things about the atomic physics as far as the atomic physics is concerned. So this is the end of slide number 4 of the course on atomic and molecular physics.